Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss a new topic regarding the flow through pipes and the loss of energy in pipes. So previously already we have discussed a few things regarding the flow through the pipes. In our previous video lectures, we have discussed about the laminar flow and turbulent flow when the fluid is flowing through the pipe. And now we'll see when the fluid is flowing through the pipe, what are the losses of energy in the pipes. Like when the fluid is flowing through the pipe, what are the losses are identified or happened, that we'll discuss in this lecture. So previously we have seen that when the fluid is flowing through the pipe, suppose let's draw one pipe, and we have seen many effects in the pipe. Already we have discussed many things regarding this pipe flow. So suppose this is the flow is there, or this is the fluid is flowing with some velocity is there. So when it is entering to this, what are the effects are there in this pipe, and whether the fluid is laminar or whether the fluid is turbulent or transition. So that everything we have identified. We know that how to identify these things. So there we have discussed in detail. So actually these things will be identified from the Reynolds number. So Reynolds number equal to, we know that rho v d by mu, inertia force by viscous force, or we can write Re equal to Vd by nu. Okay, in these two methods we can calculate the Reynolds number. If the Reynolds number is within 2000, then we can say this is laminar flow. If it is more than 4000, then it is called turbulent flow. In between 2000 to 4000, that is called transition flow. Okay, so these things already we have discussed. Now we'll see when the fluid is flowing inside this pipe, what are the losses happen in the fluid. So that is called the loss of energy in the pipes. So this loss of energy, actually due to this loss of energy, so many effects are there. Like we can see there is some pressure drop in the fluid. Okay, so pressure drop in the fluid means what is the pressure at the inlet condition of the fluid when it is moving out, or it is leaving out from this pipe. So there is some pressure will be there. If you see the pressure between this inlet and outlet, you will get some differences out there. So why this pressure difference is happening? And again, due to this loss of energy also, we used to get the efficiency, the decrement in or decrease in efficiency also used to identify in this loss. Along with that also, we can say due to this loss of energy, there is a flow rate or flow rate decrement will be there. There is decrease in flow rate. And similarly also, though the flow rate is decreasing, okay, so because flow rate is directly related to this velocity, we know that q equal to av. So though the velocity of the fluid is decreasing, so here we need more pumping effect. Okay, so pumping effect should be more to make it flow. So for pumping effect more means again cost is going to be increased here. So again one more point will be there, pumping cost will be more. So these are few things which are affecting due to this losses. So what is this losses of energy in the pipes? This is actually the loss of energy is actually divided into two categories. So one is major loss, another one is minor loss. Okay, so major loss used to happen due to friction. This is happening due to the friction. Okay, the friction, and we can calculate these things, that the major loss, with the help of, we already have discussed one thing, that is Darcy-Weber's equation. WEISBSH. Darcy-Weber's equation. Another one is Chase's formula. Or Chase's equation. By this, we can able to calculate the major loss in the pipe. And now this is minor loss. So minor loss used to happen, so many reasons are there for this actually. So you can say that sudden expansion, when the pipe is suddenly expanded. So you can write this is sudden expansion and sudden contraction. Sudden contraction. And again we can say that if there is some bending in the pipe, so there is some bending in the pipe means due to this bend in pipe also there is a minor losses is to happen. Along with that also we can say, we know that in the pipe lot of fittings will be there, so due to these fittings also some losses is to happen. And along with that we can say also due to the obstruction in the pipe, if any kind of obstruction was identified in the pipe when the liquid is flowing through the pipe, then due to that also there is a losses used to there, and all these losses are considered in the minor loss. It's very small number. But coming to this major loss, okay, which is happening due to the friction, so that is to give more impact in that. And why, how this friction, that means when the fluid is it is flowing through this pipe, so due to this pipe surface, okay, the pipe surface is there and the fluid which is flowing, so between this fluid and this pipe surface there is a friction is there, and due to this friction of this surface in the pipe, so it will obstruct the fluid flow. So how it is obstructing, already we have discussed previously, like if you see at this boundary zone we have the velocity is 0, that means negligible velocity. We can say the fluid is nearly stationary. The fluid is nearly stationary condition. Okay. Now, if you go to a little bit up here, then you can say it is moving slowly. It is moving slowly. Again, if you go a little bit more, like a little bit next layer to this one, then we can say this is compared to this one a little bit more speed. Okay, slightly slow, you can say. Slowly, then this is slight slow, you can say. And next, if you go to the next one, then you can say this is moving with this high velocity. So again, same thing will be come from here also. Okay, so that's why we used to get the our velocity profile in this pipe flow like this. Okay, now this is all about this because many effects are there due to this, because we know that there is a viscous effect is there, like viscosity of the fluid, that effect also there. Again, about it's depending upon the surface roughness, this pipe surface, how the roughness of this pipe is there. So due to that also this major loss is to consider. So this calculation of this major loss already we have seen in our last previous video lectures about the Darcy-Weber's equation, and there we have derived this equation and we have identified the head loss. Okay, so this Darcy-Weber's equation given the head loss equation, and the formula is HF equal to, we know that 4 LV square F is there divided by 2dg, and here the HF is the loss of head due to the friction. This is HF equal to loss of head due to the friction, and here the L is the length of the pipe. What is the length of the pipes, suppose, and D is the diameter, and V is the average velocity you can consider here, or the velocity is there, velocity of the fluid, and F is the friction factor, or you can say the coefficient of friction what we have taken. And this coefficient of friction, actually this value of this F will be depend on the Reynolds number, because we have seen for the laminar flow, this coefficient of friction will be is a function of Reynolds number we have seen previously, and there we got this F equal to 16 by RE, 16 by RE, and for when RE is less than 2000, that means when the flow is laminar flow, when the flow is laminar flow. Similarly, it will be different for the when the flow will be turbulent. So for turbulent condition, we can say this F equal to, another one formula was there, that is 0.079. This already we have discussed previously. Just I'm reminding this things to you, like you can recover the what we have studied. And here, when the Reynolds number is more than 4000, and up to 10 to the power 6, 4000 to 10 to the power 6. If the value is there, then we can use this value friction factor of this. So remaining things we have already discussed previously. So I hope you understand this. Now here, the next thing is, that is Chase's formula or Chase's equation. So this Chase's equation also, like, we need to derive from the previous where we have like how you got this formula. From that equation only we need to derive. So if you remember that equation, or if you have not seen that one, once you see that video, so that you can understand how we have got this head loss equal to 4f lv square by 2 dg. Now here again, before getting this value of hf equal to 4f lv square by 2 dg, we got the hf value. I'll tell you that one. That equation was there actually. Before coming to the final conclusion, we have an equation there, hf equal to, in terms of f dash, okay? So f dash by rho g into p by a into l into v square. So this was one equation which was we have derived in that time. So this one we can give in equation 1. Okay, so here again similar thing, hf is the head loss is there, we know the same thing concept, and remaining value we know that area of the cross section of the pipe, and this is the weighted perimeter. That means at what portion that water is covering, weighted perimeter, and this is length of the pipe, and this is the average velocity or mean velocity of the fluid flow. So these are the constants are there. Now we'll take one ratio. Okay, let's consider one ratio, that is A by P. A by P is nothing but, as I told you, this is area and this is weighted perimeter, and we can write this perimeter of this. Now though we are considering for the pipe, so we can write this is A by P. Okay, and you can write this concept, actually this ratio, this area by perimeter, this ratio is called your hydraulic mean depth. Hydraulic mean depth, and that used to indicate by m, a small m. Okay, that used to indicate by small m, and this is also called as hydraulic radius. Hydraulic radius. So how to identify this hydraulic radius? By this area of this pipe and the weighted perimeter of the fluid. So now these things we can write here. The hydraulic mean depth m equal to, we know that area pi by 4 d square. Again this perimeter we can write, what is the perimeter of this? Now pi by d. So we can get here dd will be cancelled, like 1d will be there, and pi will be cancelled, 4 will be in the denominator. So you can write this is d by 4. Okay, now put the value of this a by p equal to m in the previous equation, and here if you see the equation, here p by a is there, not a by p, and so what we'll do, we'll just put the value of a p by a equal to 1 by m, and so that we can write hf equal to, what was the equation, f dash by rho g into L into v square into 1 by m, because here we have taken the area by perimeter. Now in this equation we have the perimeter by area, p by a was there, so that's why I've written 1 by m. Now again same thing we can write in this way, like yeah, so let consider this velocity in one side. So this velocity square, let take it one side, and remaining terms let take it to other side. So that means we can write what, hf into rho g by f dash, rho g by f dash, v is there, L, so that will be 1 by L. So here we can write m is there, so m also will be go up, so you can write here this is m by L, f dash by rho g, so rho g by f dash, L denominator, v square is there, M is there. Okay. Now again, same thing we can write in this way, like V square equal to rho G by F dash square into M, and this is HF by L. And now if I write this V, the square, I'll take it and I'll make it a root over of this. So V equal to root over of rho G by F dash into M into HF by L. So now again here I can write these things, that rho G by F dash I can keep is a Chg constant. So let's put the value of C equal to rho G by F dash. So this is one, and another one is that we can write, yeah, what we can write here, HF by L. So HF by L also we can write, this is head loss per unit length. So this one we can write I. Let keep a value of like parameter of I and put the value of C equal to this one. So what we can write here, root over of rho G by F dash, what we can write, C. So that means V equal to, we can write C on place of this C, and this will be inside that M into, and this term is I. So I is nothing but the head loss of head per unit length of the pipe. So this equation is our final equation for the Chages equation, and this is nothing but V equal to C into root over of M, and M is the Chages constant. M is a Chages constant, and this is I equal to head loss per unit length. So this is our equation for Chages formula. So these things also we have taken by like previous derivations where we have started there. So this is all about the major loss. Okay, when there is a pipe, fluid is flowing through the pipe. So as I have told you that due to the friction, there is a major loss is there in the pipe flow, and due to the losses, what are the other effects will be there, that also we have discussed. And so in this major loss, two things are there to calculate this major loss. One is Darcy-Weber's method, another one is Chages method. So Darcy-Weber's method already we have derived previously and we have already discussed, and now in this we have discussed about the Chages formula or Chages equation, how to identify the major loss, or how to identify the losses in the pipe when it is major loss or due to the friction. So I hope you understand this theory and concept. If you are having any doubt and query related to this, you can give a comment on the comment box. Thank you.